The 1991 Saturn combines the best features of proven automotive technology to provide both dependability and state-of-the-art systems technology in one attractive package. As an experienced technician, much of what you'll see in this training video will be familiar to you, but you'll also see many features that are unique to Saturn, and we're going to concentrate on these unique features. In this video presentation, Driveability Diagnosis, we'll cover System Overview, Fuel Delivery, Ignition, Engine Sensors, Idle Speed, Fuses and Relays, Exhaust System, and Emission Systems. For 1991, there are two Saturn four-cylinder engines available: the double overhead cam with multi-port fuel injection and a single overhead cam with throttle body injection. All the major operating systems of both engines are controlled by the Powertrain Control Module, or PCM. We'll talk more about the PCM and electronic controls later, but first let's examine the engine operating systems, beginning with the fuel system. Throttle body injection, or TBI, uses a single fuel injector mounted in a throttle body that is attached to the intake manifold much like a carburetor. The TBI unit, much like a carburetor, vaporizes fuel, mixing it with air as it enters the intake manifold. The double overhead cam engine uses an arrangement called multi-port fuel injection, or MFI. MFI uses 4 fuel injectors, 1 per cylinder. The fuel injectors are mounted on a common fuel rail. Fuel pressure is supplied to the rail by an electric pump that we'll see in a moment. All 4 fuel injectors deliver fuel at the same time. In an MFI manifold, only air passes the throttle plate. The fuel injectors add gasoline at the end of the lower intake manifold runners, right at the cylinder intake valves. This provides an even distribution of the air-fuel mixture. To see the rest of the fuel system, we'll have to look under the car at the tank, pump, and fuel lines. These components are the same for both fuel injection systems. Saturn uses a high-density polyethylene fuel tank. To drain the tank, disconnect the negative battery terminal and relieve the fuel system pressure. Then block the front tires and raise the rear of the car about 28 inches, measured at the bottom of the bumper. This allows the gas in the tank to drain to the front, leaving the connections clear. Now, at the tank, loosen the filler neck and vent clamps. Wrap a shop towel around the necks to soak up any spills and remove the tubes from the tank. Use an 18-inch socket extension to push the check ball into the tank and siphon the gas from the tank into an approved container. Then raise the car all the way up and remove the tank. Before you reinstall the tank, remove the fuel pump module and push the check ball back into the filler neck. See your service manual for tank removal. An electric fuel pump in the tank supplies fuel to the injectors. The PCM controls the pump. Fuel pressure in the TBI metering assembly and MFI fuel rail varies from just under 30 to just over 40 psi, depending on the engine demands and operating conditions. Saturn uses a unique fuel pump module that adjusts its own position, allowing the pump assembly to remain on the bottom of the tank to compensate for the minor inflation and deflation that occurs in a polyethylene fuel tank. The fuel pump module is non-serviceable. It should be replaced as a unit. However, the sending unit is serviced separately. If you have to replace a fuel pump module, use the sending unit from the original module. Saturn fuel lines deserve your special attention. They're made of nylon for corrosion resistance. You'll find them easier to work with than steel lines, but it's important not to kink them. If they become kinked, replace them immediately. All the fuel fittings except 2 are the quick connect type. They can be disconnected and reconnected without special tools. The fittings at the fuel rail require you to use special tools, just like the ones you may already be familiar with. These fittings have internal locks for a more positive connection. To separate the fitting from the fuel line, push the correct fuel line tool into the fitting like this, while pulling gently on the hose. The hose should separate easily. Before attaching a quick disconnect, lubricate the male end with engine oil. During attachment, listen for an audible click, then pull back to confirm engagement. Now let's take another look at the fuel rail and injectors on the engine. The gasoline coming from the fuel pump and filter enters the fuel rail here. Its pressure is controlled by the pressure regulator. Fuel is then routed to all 4 injectors through the fuel rail assembly. Each time the PCM signals the fuel injectors to open, the pressurized gasoline is sprayed directly at the intake valves. The PCM triggers all injectors once for each crankshaft revolution. As each intake valve opens, a precisely measured amount of fuel is available for that cylinder. This arrangement permits the PCM to tightly control the air-fuel ratio during all engine conditions. Now let's examine the Saturn ignition system. The Saturn car uses a distributorless ignition system, or DIS. Instead of a distributor, DIS uses a coil pack containing 2 ignition coils, each of which controls 2 spark plugs. The ignition coil and ignition module are all in one assembly. The module is controlled by the PCM using inputs from the crankshaft position sensor. We'll talk more about the sensors later in this video. There is one other unique feature of the Saturn DIS coil. Unlike other DIS coils, the Saturn ignition coil allows you to perform a coil spark test. Just take the spark plug wires off the coil and crank. Since the Saturn uses a gear reduction starter, be careful never to crank it for more than 15 seconds. This test has been prohibited with other DIS coils because it could cause damage. But the Saturn coil has been designed to allow this test, so you have an easy way to tell if the coil is producing a spark. Now let's see how the PCM controls the engine operating systems. The PCM actually controls engine systems, the automatic transaxle, and EBO steering. However, in this video, we're going to concentrate on the engine control functions. The PCM is located behind the instrument panel at the extreme left side right next to the bulkhead. It can be reached and easily removed by using a screwdriver. To replace it, simply snap it back in. The PCM receives information from sensors at various locations on the powertrain. It uses controlling equations, called algorithms, to make decisions based on that information. Those decisions control the PCM's output systems, such as the fuel injectors, electronic spark control, and the different emission control devices. The electronic control system uses several sensors that may already be familiar to you. These include the crankshaft position sensor, the throttle position sensor, the coolant temperature sensor, the air temperature sensor, the manifold absolute pressure sensor, the oxygen sensor, and the AC on and power steering pressure signal inputs. Let's quickly review the operation and purpose of all these sensors and see how they work together. Some of them are a little hard to see on the car, so we've gathered them together here. Let's start with the crankshaft position sensor, which is used to control both the fuel and ignition systems. It is a variable reluctance sensor, which means it produces an alternating voltage as a reluctor ring on the crankshaft passes by it. The crankshaft position sensor output goes directly to the ignition module, which converts it to a square wave and sends it to the PCM. The faster the crankshaft turns, the higher is the output frequency of the sensor. The powertrain control module reads this input as engine RPM and determines how often and how quickly to operate the fuel injectors and ignition coils. The throttle position sensor is a variable resistor connected to the throttle linkage. The TPS tells the PCM what the driver is demanding from the car: idle, cruise, wide open throttle, and everything in between. The position of the throttle plate directly controls how much air gets into the intake manifold. The throttle position sensor tells the PCM the throttle plate's position by providing a variable voltage signal. If the throttle is closed, the throttle position sensor returns a low voltage signal. As the throttle opens, the throttle position voltage increases. The highest it should ever be is about 4.8 volts. You'll notice that the sensors that use reference voltage such as the throttle position sensor, have operating ranges that never go to 0 volts nor to the full 5 volts. These are called deadband sensors. The low and high sides of the operating range tell the PCM if there is a problem with the sensor or the sensor's electrical circuit. If the voltage output of one of these sensors ever goes below 0.2 volts or above 4.8 volts, the PCM knows that there is a problem with that sensor circuit, and the output signal can't be trusted. The PCM will then set a diagnostic code or information flag, light the service engine soon telltale, and ignore the input from that defective sensor circuit. The PCM will then operate the vehicle using default values or other sensors to determine a best guess value. There are two temperature sensors, the coolant temperature sensor, or CTS, and the air temperature sensor, or ATS. Both are thermistors, temperature-sensitive resistors. The PCM supplies voltage to each temperature sensor. The sensor then reduces this voltage by varying resistance to ground. The voltage variation depends on the temperature that the sensor is exposed to. As the temperature rises, the voltage falls. So the higher the temperature, the lower the voltage you read. Although both thermistors work in the same way, they're doing slightly different things. Of the two, the coolant temperature sensor has the more important job. The temperature of the engine is determined by measuring the temperature of the coolant. In a cold engine, fuel vapor in the intake manifold tends to condense back into a liquid state, which won't burn. The coolant temperature sensor sends the temperature information to the PCM, which then compensates by causing the fuel injectors to deliver more fuel when the engine is cold. As the engine warms up, more and more of the gasoline stays vaporized. The coolant temperature sensor relays this information to the PCM, which commands the fuel injectors to deliver less fuel to the engine. So, the engine doesn't run too lean when it's cold or too rich when it's warm. The action of the air temperature sensor is a little more involved. In closed loop, the PCM maintains a balanced air-fuel ratio. To do this, it has to know how much air is in the manifold at all times. The volume or mass of air is determined by two factors: manifold pressure and air density. Cold air is more dense, but as it warms up inside the intake manifold, its density decreases. So if the air temperature sensor sends a signal to the PCM indicating a warm temperature, the PCM knows that there is less air mass present. That information goes into the calculations that are used to determine fuel injector pulse width, or on time. We've seen the sensors that measure engine temperature. Now let's look at the sensor that measures engine air pressure. On the double overhead cam engine, the manifold absolute pressure, or MAP sensor, is located on the intake manifold. On the single overhead cam engine, it's mounted on the rocker cover and is connected to the manifold with a vacuum hose. The MAP sensor is a resistance-type device that returns a voltage signal to the PCM. The signal varies directly with the air pressure in the manifold. When the air pressure in the manifold is low, such as at idle, the output voltage of the MAP sensor is also low, about 0.5 to 0.9 of a volt. When the manifold pressure is high, such as at wide open throttle, or when the engine isn't running at all, the MAP sensor voltage is also high, about 4.8 volts. Of course, this will vary with altitude. In Denver, for example, the highest voltage you'd see would be about 4 volts. Pressures between these extremes produce corresponding voltages from the MAP sensor. As with any of these sensors, look in your service manual for the actual specifications. The oxygen sensor is used in closed loop to determine the rich or lean state of the air-fuel mixture by measuring the oxygen content of the exhaust. If the air-fuel ratio is lean, the exhaust gas contains very little unburned fuel vapor but a lot of oxygen. When the oxygen sensor detects a high level of oxygen in the exhaust gas, it sends a low-voltage signal to the PCM, about 0.1 of a volt, which the PCM interprets as a lean air-fuel ratio. If the air-fuel ratio is rich, the exhaust gas contains a large amount of unburned hydrocarbons, but very little oxygen. When the oxygen sensor detects a low level of oxygen in the exhaust gas, it sends a high-voltage signal to the PCM, about 0.9 of a volt, which the PCM interprets as a rich air-fuel ratio. If you're getting a consistently high signal from an oxygen sensor, it's probably not an indication of a faulty sensor, but instead a rich air-fuel ratio. Something else to remember is that any time the oxygen sensor is cold, or if it becomes disconnected, it won't send a signal at all. The last two inputs or signals we'll cover are the AC on input and the power steering pressure switch input. These help the PCM control the engine's speed at idle. The PCM uses the idle air control valve to control idle speed. Normally it keeps the idle speed within a certain range, high for a cold engine, lower for a warm engine. But it needs to compensate when additional loads are about to be put on the engine, loads such as the air conditioning or the power steering. The AC on and power steering pressure inputs tell the PCM in advance of these increasing loads so that it has time to compensate for them. If any part of the electronic control system fails, the PCM will be aware of it and take steps to prevent the fault from seriously affecting engine performance. It will signal the driver of the problem by illuminating the service engine soon light, and it will store a diagnostic code in memory. As with other systems, you can get the light to flash any stored malfunction codes. See your service manual for the exact procedure. The Saturn car has fuses and relays at two locations, the instrument panel junction block and this under-hood junction block. Let's have a look at the fuses and relays that pertain to the systems we've seen so far. The Ignition 4 maxi fuse supplies system voltage to most of the other fuses related to our fuel and ignition systems. Ignition 4 is hot when the key is in the crank or run position. If this fuse fails, the engine will crank but will not start. The ignition coils and modules are supplied by this 7.5 amp DIS mini fuse. Check here first if there is no power to the ignition system. All four fuel injectors are supplied by this 7.5 amp injector mini fuse. If there is no power to any of the injectors, check here first. There are two mini fuses for the PCM. PCM 1 supplies the switched 12 volts to run the PCM itself, reference voltage, and some of the output circuits. PCM-B has voltage at all times and is used for the keep alive memory. This instrument panel junction block, which is located on the passenger side of the instrument panel central column, contains 20 mini fuses and 4 relays. This 10 amp mini fuse supplies power for the fuel pump. The fuel pump itself is operated through the fuel pump relay located here. A unique feature of the instrument panel junction block is this probe hole, which allows you to test the fuel pump circuit without removing the relay. Simply insert one voltmeter probe into the hole, ground the other probe, and turn the key on. Be sure to use a digital voltmeter. You should read a 12-volt DC signal for a few seconds as the PCM turns the pump on and off. Since we're talking about unique Saturn features, we need to have a quick look at the exhaust system. All of the exhaust pipes on the Saturn are stainless steel for additional durability, and the connection between the exhaust pipe and manifold is made by this stainless steel flex pipe. That brings us to the emission systems. Let's take a quick look at the EGR and charcoal canister purge systems. The EGR valve operates in a way similar to those you're familiar with. It's controlled by a ported vacuum signal from the throttle body. The PCM closes the EGR valve by energizing this normally open EGR solenoid, which shuts off the flow of vacuum. The purge solenoid shown here is operated by the PCM at specified times to purge the gasoline fumes from the canister. Likewise, the charcoal canister purge system is very similar to systems you have seen on other cars. The canister is located inside the right front wheel well. You can service it through a removable panel. In this video, we've seen a quick overview of Saturn's engine systems and their components. The fuel system in its two varieties, throttle body injection and multi-port fuel injection. The distributorless ignition system. The powertrain control module. The electronic sensors. The exhaust system. And the emission systems. As a Saturn technician, you will have the latest generation in diagnostic equipment, which will make the job of electronic system diagnosis easier than it's ever been. Practice with this equipment today, but any diagnosis has to be founded on a complete understanding of how the system works and how the different systems work together. Don't assume that the computer will do the job for you. As good as the hardware is, there's still no replacement for you. It's the combination of the Saturn automobile, Saturn diagnostic tools and procedures, and you, the trained Saturn technician, that forms an unbeatable team.